Um, Acoustics, sir. Aquasis, sorry.
Page number.
Page number 56. Sorry, 59, sir.
So what is the sound wave?
So,
Does it require a medium for propagation?
okay, sir.
See, basically, you have to see this is a
Mm,
speaker which is emitting sound, and here
mm,
the human ear. So when this speaker vibrates, the air in contact with that, it will also vibrate in the sense like when this speaker is coming out, it will push the air, so it'll get compressed.
mm,
Okay, so this
mm,
whatever is membrane, it will see for some time it will come out. Just a minute.
mm,
This membrane for some time will come out, and then
mm,
it'll be here and then it'll go in, right? So when it comes out, it will push the air. Okay, when it goes in,
mm,
it's sort of creating a vacuum. So basically, the
mm.
air will get compressed and then rarefied. Okay,
Okay,
so
sir.
here the density will be
Uh,
more, the density will be less. It will be more. So basically, that vibration will get transmitted
mm,
to this ear.
mm,
Okay, and inside ear there is a drum,
mm,
ear drum. Okay,
mm.
so this air will go and hit this drum, and this drum will vibrate, similar to the vibration here.
Okay.
It's also a drum, right? It's sort of membrane which is
Yes.
vibrating. This will get passed to the
Mm,
ear, okay, and it will go
mm,
and hit this eardrum, and the eardrum will vibrate, and that sensation will be picked by the brain.
mm.
Okay, so that's how you hear the
Oh,
noise. So suppose this
mm,
medium is air is not there, suppose it's
mm,
vacuum, then
mm,
sound cannot be travel,
mm.
but light will travel in vacuum.
Okay.
Okay, so suppose there are two people sitting in a room where there is no air.
Mm,
Okay, the two people can see
mm,
each other because it's light, right? Seeing means this light has to go from one person to another person, but they cannot hear even
mm,
if they speak
mm.
because air is not there.
Ah,
So in some sense, I don't know whether they use it's called matter wave, sound wave, because it
mm,
requires medium for propagation. And of course, this frequency
mm.
can change the variation with the time. So from here to here, what is the thing called?
Wavelength, sir.
No, it's a time variation, right? Something as a function of
Ah,
time. The time periodicity
mm.
is capital T. Okay. Similarly, some things can vary with space also. That
Ah,
periodicity is lambda.
lambda. Okay.
What is lambda?
Periodic timing.
Periodic space periodicity. Wavelength.
Space.
Have
Basically.
we used lambda or some other symbol for wavelength?
Mm.
We have said wavelength. What is the symbol for wavelength in the book?
The opposite of Y.
Um, Lambda only.
Ah.
Correct. Okay. So
Mm,
basically, see, something varying as a function of space. Let me take space as x
mm,
variable, one dimension.
ah,
So something is varying as
mm,
space. So this is the
ah,
variation time t naught, initial time.
ah.
Yeah, time t1, the variation has moved like this
Okay.
at time t1. So this is a traveling wave.
Mm,
With
mm,
time it's traveling. So this is actually a wave.
mm,
It's both function of time and
ah,
space. But
mm,
since I can denote only one thing in this graph, because one is x variable, the thing will be
mm.
property, either pressure or something, pressure or density. Okay, I cannot represent the third variable. The third variable represents
Okay.
as a parameter. So this is for
Ah,
T naught, The next plot round is for T1. Next one will be for T2, like that. So from there, I can figure out with time what's happening.
Okay,
Okay.
sir.
So with respect to space was the relation, and also with respect to time, means I have to fix a point in space and see what is the value of at T0 this much is the value, at T1 this much is the value. Okay. So if you
Okay.
plot the thing again, it will be a sign variation only. So this
Mm.
periodicity is time periodicity.
Ah,
And this
okay.
periodicity is period in space, that's lambda.
Mm.
Okay. And velocity is, if suppose I stand here, this wavelength lambda will
Ah,
travel in amount of time
ah,
completely.
okay.
So, and this, from this only I get the formula. And 1 by t is frequency.
Mm.
Because in, suppose this time period is say 2 seconds from here to here.
Mm.
That means
Mm.
in 1 second, how many vibrations will be there? Half,
Half the vibration.
right? Suppose this is 0.5
Yes, sir.
seconds, then in 1 second, there will be 2
Mm.
vibrations. So frequency is 1 by t.
1 by. Okay.
That's a basic formula.
Mm.
Another formula is velocities in one time period, the amount of distance this thing will travel is lambda.
Mm.
So this is usually this what is remembered velocity is frequency lambda, and you have to remember that frequency is 1 by time period. Velocity is distance by time. It will travel distance of one wavelength in a time of capital T.
Mm.
Okay.
Mm.
And another basic thing is frequency is 1 by t.
Mm.
So you can remember this one and also
Mm.
this one.
Mm.
With these two, you'll get the other ones. Okay, velocity, frequency, and wavelength. Given the space periodicity, frequency is 1 by t, and the time is time periodicity. Okay.
Sorry, sir.
And velocity of the light will change with medium. In denser medium, it will go slower. Like in air and glass, that you already studied in the light chapter, right? Velocity in glass is less compared to velocity in air. Okay, so even solid is obviously more dense, right, compared to liquid, and liquid is more dense compared to gas. So velocity is fast in solid.
Mm.
Because I take a iron bar and hit it here, it'll go very
Mm.
fast. But if it is gas, means it's some sort of cushion is there. Okay,
Mm.
so it will go slowly.
Mm.
That way you can understand. Liquid is in between.
Okay.
Okay, famous practical example, there is a rail track, there is a train
Mm.
here. Okay, so from
Mm.
a person is here, so the train moving, it makes some noise, right? Either whistle
Yes,
or
sir.
vibration of the track or something. So that sound will come like this in air.
Mm.
Another sound, if you keep your ear on the track, which is made up of iron, sound will also
Okay.
be this one. So this
Mm.
sound will reach you far first. So if this train is very, very far away, if you
Okay.
place your ear on the track, you will hear
Mm.
the noise because this will take some
Okay.
time to reach
Mm.
because this is solid and this is air. Velocity
Okay.
sound is more so you will so when it's very far away, this sound will come you first,
Mm.
reach you first.
Okay. It depends on the how fast it comes, sir.
No, no, just that whatever is that motion is creating some vibration on the track. No, similarly create
Ah.
vibration in the air also.
Okay.
Okay, even if you take a paper and
Mm.
uh, shake it like a viscery, it will make some noise,
Mm.
right?
Yes,
Okay,
sir.
the thing is creating the disturbance in the air molecule.
Mm.
Similarly, a moving object will create a disturbance in the air surrounding it.
Ah.
Okay, so that sound will travel and reach the this thing, and there is vibration here also, right? It's not
Ah.
just smooth, there will be vibration here. So
Mm.
that vibration also travel. But this is traveling
Mm.
solid, this is traveling gas, air. So this will reach first.
Okay.
This sound requires a medium. This can travel in vacuum. Example is sun. Between sun
Mm,
and earth, earth surrounding the earth, there is atmosphere, but here there is vacuum,
mm,
and here there is sun. So it's able to pass through this, right? So that means
yes.
light don't require a medium.
Mm,
Okay, once it reaches here, it will go through that atmosphere, but
mm,
light can travel through the medium not
ah,
required. Okay, but
ah,
sound, uh, if two people are
mm,
there, there is a vacuum in between them, then it won't propagate because sound is basically the air molecules vibrating and going hitting the
ah,
ground.
okay.
Suppose this air molecule is not there, then what will go and hit the eardrum? Nothing.
Mm-hmm.
Okay, and sound waves are longitudinal. This you know.
Mm. Yes, sir.
Yes. See here,
Mm,
this thing air molecules are the vibration of air molecules will be in this direction, matching with this
mm,
one.
yes, sir.
Okay, so directional vibration is this one.
Mm, sir.
Hold on. Huh. Yeah, it is matching with the direction of the and propagation of wave
Mm,
is in this same direction. Both are
okay.
same direction. This vibrating like this
Mm,
is 0 degrees, 180 degrees. So this is longitudinal waves. But
mm,
suppose you take this water, okay,
mm,
and you drop a stone, okay, it will
mm,
form rings, right? And these rings will go out.
yes,
So wave
sir.
is going like this, but the water molecule here is vibrating in this
Mm,
direction. Suppose you put a
mm,
floating object cork or something, the cork will
ah,
vibrate up and down in the same place.
ah,
Here also, this air here will not need not move here.
mm,
The air will just vibrate and stay here itself.
okay.
Okay, the medium need not move. Just the information has to move. Suppose there are you are here
Mm,
and your friend is here. Between there are some other people. You are passing
mm,
some message on the ear of this person. So this
mm,
person will pass the message to the next person, next
mm,
person. But the person here is not moving.
mm,
Only the message is moving.
ah.
Okay, so this
Like
is
that, the vibration moves on.
so this suppose I mark this thing as red molecule.
Mm,
Red molecule will
mm,
just be here only, but it will just go back and forth. This
okay.
motion will get transmitted here. Because of this
Mm,
motion, here also it will vibrate back and forth, here also it will vibrate back and forth.
okay.
Okay. So here it is vibrating at frequency of 5 Hz, same 5 Hz will go here.
Mm,
So this is an example.
mm,
There's a queue of people who are passing some
mm,
message. This message is
mm,
passed to the next person, but the person is not moving. The person is staying here only.
mm,
Only the information is moving, but the message is moving.
mm,
Okay, so this is how the wave moves.
mm,
The air can be standstill, but of course, this microscopic motion will be there.
mm.
Transfer. Light waves are transfer. Light waves is basically electrical wave,
Mm,
and propagation will be like this. And
okay.
magnetic, it's combination of electric and magnetic field. Okay, this you learn in
Ah,
your 12th standard or 11th, 12th standard. Okay, but basically you have to
ah,
understand electric field vibrate in this direction, say Y direction.
mm,
Okay,
mm,
and propagation is in X direction, and in the Z
mm,
direction there will be magnetic field vibration.
o- okay.
So X is perpendicular to both Y and Z, and the wave is basically vibrating
Mm,
electric magnetic field.
mm,
Okay, so here the vibration is perpendicular, but the
mm,
wave propagation is perpendicular. Like here
okay, sir.
in this water,
Mm,
the
mm,
stone, the waves are moving out, but the water here will just oscillate up and down.
mm,
It's perpendicular, this vertical, that movement is
mm,
horizontal, 90
okay.
degrees.
Mm,
Transverse is 90.
mm,
Transverse. Okay. So wavelength ranges from 1.6 millimeter to this
mm,
one. Okay, this wavelength is completely different. This is wavelength of this one. Electromagnetic, this is this sound wave. Okay. This is small, 10 to the minus 7. This is centimeter and 2 meter.
mm,
Sound waves travel in air at a speed of 340. Light wave reach at
mm,
the speed
mm,
is much higher. So the sound velocity of sound depends on the Suppose it's traveling here, it depends on temperature, pressure, density. Factors affecting sound, one by density. So you should remember the formula is one thing, but you also understand the formula. So this means if it is density is more means velocity will decrease. This is for the case of gas.
Okay.
You cannot compare gas and solid. Say solid is more dense, so velocity will be less in that. It's completely different. Just if you take the case of gas and there are two gases, density is increasing means velocity will decrease.
Okay.
Okay. Temperature, if it increases,
Uh,
velocity is increasing.
okay.
Okay. Increases with increasing temperature. It's a square root of
Okay.
humidity.
Uh,
Humidity increases, then sound increases. Humidity increases, water molecules are there. So obviously density will go up. If density goes up, velocity will go down, but he's saying opposite. Okay, there could be some other reasons. Okay, don't compare with density then.
Okay.
So if it is wet air means it will travel faster.
Okay, sir.
So obviously means solid, the sound is 5,000, something like that. Liquid is 1,000. Gas is less 300. The velocity is equal to the square root of temperature. Temperature variation will be to density is there. Yeah, square root of temperature. Okay. Velocity will be square root. So V2 is proportional to T2. And temperature should be in Kelvin. Okay, so whatever is in degrees Celsius convert to Kelvin by adding 273. So sound like light wave, this also can get reflected by the wall. Okay.
Okay, sir.
So again, this thing is where I equal to R. Last topic is Doppler effect, is it?
Yes, sir.
13th is your test. So only tomorrow you have, is it?
Yes, sir.
Okay. Actually, CBC, the portions are less, but problems will come. Here, theory part is more, but problems will not come. So this is one thing, reflection, loss of reflection, I equal to R. And after that, and a denser medium. So basically, it's going and hitting like this, and there is after reflection, there is a phase reversal. See, this is wave is going and hitting the wall. After there will be
Okay.
reflection, right? Like here, what are these? There's a reflection, right? But suppose I send the wave like this, come back like this, because this case corresponds to I equal to 0 degrees, which is equal to R. I equal to R is a law. In this particular case, going straight, it's along the normal, so it'll come out straight. So that's what is happening here. Here is normal, this thing. So I equal to R, so it's coming out straight. So, but when it's reflecting, the thing is getting ulta, like phase reversal is there. If it is a rigid wall. Okay, but suppose if it is narrow, again there is reversal. Here it's at R equal to minus F, so there is a reversal.
Hmm.
Okay, this I have to check. See, in tensor will be reversal, but in
Hmm.
what is this thing here? Is it they have written rare medium, right?
Yes, sir.
What they have written here? Figure itself is not clear. Here you can see the thing which is up here after reflection is going down. Okay. And then one thing we can say is what is sitting here is a compressed one, up one. But here in this case, what is sitting is the
Hmm. F.
here also it's like up one only sitting. After that, it's reversing as low one.
They
But
both are same now.
but the color is different. Here you put this green, green
Ah.
hitting and then green coming down.
Hmm.
The green hitting and orange is down.
Okay.
Okay, I'll let you see.
Hmm.
Here in the figure it's clear. See here, it's dense, right? They have some like a
Ah.
dark this thing. So here density is high. When it's reflecting, it has become rare.
Hmm.
Okay, but here density is
Hmm.
high, it's reflecting as dense. So I think this figure is wrong. It should be like this only.
Hmm.
Okay, you can just Google and check. Reflection by a density
Okay.
medium and reflection by a rarer medium.
Sir, but if the denser medium gets higher, they both look same, no?
And good.
Okay.
Medium. Okay, let me not waste. I'll tell you tomorrow. Okay.
Okay, sir.
Reflection is basically echo.
Hmm.
And one more thing is, see, a source, whatever, let's say, let me take a speaker itself. Okay,
Ah.
it is vibrating with some frequency symbol is
Hmm.
F, no, and there is a
Ah.
person hearing this sound. Okay, what is the frequency of the sound received by this listener?
Hmm.
Suppose say F is say 100 hertz. What is
Hmm.
the frequency of the sound received by this listener, area FL or whatever? It will be same 100 hertz. Why should it be
Hmm.
different?
Yes.
Okay, but this is true if the person is at rest.
Okay.
Okay, suppose the person is moving towards this source, then the frequency will increase. Okay,
Hmm.
if the person is walking away from the source, then the
Hmm.
frequency will decrease.
Okay.
Same thing will happen if the person is at rest, but this source of sound is moving towards the observer, listener.
Ah.
So whenever the distance between these two decreases, the frequency will
Hmm.
go up. If it is increasing because of this guy moving, or this guy can also move this way, right? Okay, either way, in some way, if the distance between these two are
Hmm.
decreasing, then the frequency will go down.
Hmm.
Okay, so the formula is
Ah.
this one. This is prime is a
Hmm.
observer or the frequency listened by the observer. This is the original frequency. Okay, suppose L is what listener and S is the source. Suppose both are stationary. Okay, then this is zero, this is zero, right?
Hmm.
Then V and V will cancel. So whatever is the frequency of the emitted sound will be listened by the
Hmm.
observer, listener. But suppose the listener
Mm.
is moving, then the frequency will increase,
Mm.
right? Say the source is stationary, and I take
Okay.
one direction as positive. So here,
Mm.
source, and here there is a listener. Okay, and origin of the x-axis is here, and this is my positive direction. Okay, let me
Okay.
assume this guy is moving in this way Vs, this guy is moving in this direction Vl.
Mm.
Okay, so according to this convention, if Vl is there means the distance is increasing, right? Then the frequency has to, mm, let me take another way around. Okay,
Okay. Ah.
then listener is here, source is here.
Ah.
You should put a diagram. Here it is the diagram is.
Ah.
Okay, source,
Ah.
if both are okay. This what you should put the proper reference. See, according to him, then this is VL, this is VS.
Okay. Yes.
Okay, so when VL is there, frequency should go up. When VS is there, frequency should go up. But since VL is the
Mm.
numerator, it should be plus.
Mm.
Uh, And VS is the denominator, right? So it should be minus when VS is there.
Ah.
Okay, I took some other convention. I took both as right. But according to
Okay.
him, he has taken this as his reference or the
Oh.
convention. Okay, so according to this diagram, this is VS direction, this is
Mm.
VL direction. So according to this time, VS is there means frequency has to go up, right? Because distance is decreasing. Bring one
Yes,
by
sir.
one. Assume this is not there, VL is not there. Okay,
Mm.
just VS is there. If VS is there, the frequency
Ah.
has to increase. And VS is the denominator, so it should be minus. Denominator
Okay.
get less, no?
Yes, sir.
Okay, only the end will go up. Next,
Ah.
forget this VS, put only this VL. When VL is
Mm.
there, this frequency has to go, and VL is the numerator, so it should be plus VL. Only the
Mm.
frequency will go up.
Mm.
Numerator by denominator, for this thing to go up, numerator has to go
Mm.
up or denominator has to go down.
Ah.
Okay. So
Okay.
according to this assumed direction, this is the formula.
Mm.
So you stick to what is there in the book. So suppose in
Okay.
the exam they are given velocity of this source,
Mm.
they say in this direction 2 meters per second, then the Vs value is minus 2.
Okay, sir.
So it becomes V plus 2. Because when it's going away, the frequency has decreased, no? So that will come if I
Mm.
put V plus 2.
Mm.
You can also check when they are moving away, frequency has to decrease. That you also can fix the sign.
Okay.
Stop. Okay, a source is producing a sound of 90 hertz. Approaching means frequency to go up. Okay, approaching station listener with speed equal to 1 by 10 of the speed of sound.
Mm.
Source is S, and there is a listener
Mm.
here. Source is producing a frequency, so N is 90
Mm. Okay.
hertz, and approaching, so it's moving like
Ah.
this. This guy is stationary, so rest.
Mm.
Okay, with speed equal to
Mm.
velocity of the source is
Mm.
1 turn. So velocity of sound, if I say C, it is C by 10.
Okay, sir.
You should not confuse its light, so I put CS. C is velocity
Mm.
of light. Velocity of sound, I know what is in the book, but one symbol is CS, just to make it clear, different from the light one. This is light, this is sound.
Mm.
So CS by 10. Okay,
Okay.
so if you use that formula, then prime equal to, it's basically listener by source.
Okay.
This is the sound speed. You can also just put plus or minus. Okay, listener, see,
Oh.
another thing you have to remember is listener in the numerator.
Mm.
This source in the denominator, this is the absorbed frequency.
Okay, sir.
Okay, so
Ah.
listener is stationary, so the listener will go, only VS will be there.
Mm.
And since the thing has to go up, it should be minus. So CS, we just say C, and this is C minus C by 10. So it is 1 divided by 9 by 10. So it's 10 by 9 of the
Mm.
original intrinsic frequency. That's 90.
Mm.
So it has increased to 100 hertz.
Okay.
So this way also can get remember the formula rather than just getting
Okay.
confused with this one. Just put plus or minus. Decide plus or minus based on if the distance between listener and uh, source and listener is decreasing, frequency has to go up. If this increasing means
Okay, sir.
frequency will go down. Here it's approaching. Okay, so frequency
Hmm.
will be more, and the thing is the denominator, so it should be less value. So it should be minus.
Hmm.
Okay, so decide this plus or minus based on physical reason
Hmm.
rather than direction, taking the proper symbol. That is not necessary.
Hmm.
Okay, source producing a frequency, so n is 500 towards, so
Ah,
that frequency has to increase. Listener with, so this is VL. Okay, speed of, so this is C or CS. Okay, so again, n prime, observed this one is listener by
hmm.
source plus or
Hmm.
minus velocity of sound plus or minus velocity of sound
Okay.
into the intrinsic frequency. Here, its
Okay.
frequency has to increase, and it's a listener,
Ah.
so it will be 360
Hmm.
by 330. Source is at rest.
Okay.
The source is moving towards us. Okay, fine. Any mistake? Listener is at rest.
Hmm.
Listener is at rest. Where is it mentioned? Source is moving, right?
Yes, sir.
Okay. Towards the listener with the velocity. He has not said listener is at rest. So we shall assume it's at rest because he has not given the speed. Okay.
Ah.
So C 330
Hmm.
and denominator has to be less because frequency has to increase. So 330 minus 30 is 300
Okay.
into 500. 550.
Okay.
Okay, source of sound moving with the velocity of 50 meters towards station listener. So VL is 0,
Hmm.
50, and it's towards.
Hmm.
So that means n prime is greater than n. So get the answer.
Yes, sir. 1 second. So is it 550? Sir?
Got the answer?
Yes, sir.
What is it?
550, sir. Hertz.
No.
Mm.
Check again.
Okay, 1 second, sir. Okay.
Listen as the numerator. N
Mm.
prime equal to VL by Vs. This is sound speed plus or minus plus or minus.
I put VL as first, sir. 1 second.
VL is 0.
Ah.
That's why you write. Once you say stationary, convert this
Hmm.
whatever is information in terms of symbols.
Mm.
You should read the question only once.
Okay.
As soon as you
Okay,
read,
sir.
convert all the information in terms of symbols.
Hmm. 1 second, sir. So is it 848.48, sir?
Yeah.
Okay.
This is the logic. Okay. Remember the
Ah.
formula, this n prime equal to n, and then listener by source.
Hmm.
C plus or
Hmm.
minus. C is velocity of sound. Okay.
Okay.
So this plus or minus you should decide based on whether it's approaching or moving away.
Hmm.
Okay, here this one, source and listener both moving towards
Hmm.
each other. Speed is v by 10. Where e is speed of sound. Get the answer?
1 second, sir. So can you repeat it one more time?
Here it's written no. Source and
Ha.
listener both moving towards each
Hmm.
other with speed v by 10.
Hmm.
Where v is
Hmm.
the speed of sound.
Okay.
And the
One
frequency of
second.
the source frequency is f.
So is it 1.22 frequency?
Yeah.
Okay.
So both the listener movement and source movement contribute to increase in the frequency. So numerator has
Hmm.
to be plus, denominator has to be minus.
Hmm.
So see source, listener, there are four possibilities. One, both are approaching.
Hmm.
So it will be plus in the numerator and minus in the denominator.
Okay.
Because both has to contribute to increase. Another possibility is source is moving, listener is also moving towards right. So source movement will contribute to increasing the frequency because it's moving towards the listener, right? It's trying to reduce the distance.
Okay.
Okay, so listener is the numerator, uh,
Hmm.
source is the denominator. So source is contributing to increasing the frequency, and this thing is contributing to
Hmm.
decreasing the frequency because so this is minus thing. Numerator is
Hmm.
minus because if you forget the source movement, listener is trying to get away. So that means the distance will,
Okay.
this thing will increase. So it will be minus minus. Another possibility is both
Okay.
are towards left. So source
Ha.
is moving away, so it will contribute to plus,
Hmm.
and listener is moving towards, so it will contribute to plus plus.
Hmm.
And the last possibility is both away away. So
Hmm.
both will be minus divided by plus.
Okay, sir.
So plus minus 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 plus plus minus plus.
Hmm.
Four possibilities.
Okay.
That's what is given here. Plus plus.
Uh, yes, sir.
Okay, here is different. One of them is zero. Okay, here is
Hmm.
different. Everybody the rest means you just have to put it zero, but basically this is these are the four things.
Hmm.
If something is zero, that term won't be there. That's all. Okay, so basically decide the sign based on understanding whether the distance is decreasing or increasing. Other things are theoretical. So suppose there is
Okay.
a reflecting wall somewhere here, and there is a source of sound here. So this
Hmm.
go here, and it is reflected
Hmm.
and reach this thing, right? So by the time it takes to um, hear the reflection, if it is 2 seconds,
Hmm.
what is the distance of this this d? So that means
Two.
if it's 2 seconds from going